Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to predict the spontaneous direction of a redox reaction. So let's get into this. So the first thing I want to do is kind of review what we talked about in the last video. So remember that you have a half reaction. That half reaction, if it's more negative or has a more negative electrode potential, it's going to then have more of a tendency to lose electrons or undergo oxidation, which is the loss of electrons. Now, if you have a half reaction with a more positive electrode potential, then that's going to have the tendency to gain reactions or undergo reduction. So that's what I have written here. So this is going to undergo reduction. And so an easy way to kind of remember this is to always remember that negative electrons are going to be repelled by negative electrode, and they're going to be attracted by the positive or more positive electrode. So all you need to do is figure out which electrode is more negative, which one's more positive, and that's the direction that the electrons are going to flow. They're going to flow from the more negative electrode with the they're going to flow from the electrode that has the more negative electrode potential towards the electrode that has a more positive electrode potential. And so that's kind of an easy way to remember. Another mnemonic device that might be helpful is NIO, NEO, and PER. So NEO and PER. So NIO stands for if more negative is oxidation. So the more negative electrode, the electrode with a more negative electrode potential is going to be the electrode that undergoes oxidation. And the electrode that has the more positive electrode potential is going to be the one that undergoes reduction. So if you can remember this, neo and pure, then that might help remember this idea. So let's use an example here. So here I have two redox half reactions. So again, normally when we write the half reactions of a cell, we are going to write them in the reduction form. So you can see that they're both in the reduction form. So nickel is going to pick up 2 electrons. So nickel 2 plus picks up 2 electrons to form nickel solid, and that has an electrode potential of negative 0.23 volts. And here we have manganese. So manganese 2 plus is going to pick up 2 electrons, and that's going to be manganese solid, and that has an electrode potential of negative 1.18 volts. And so you can look here and you can see, okay, well, this has a less negative electrode potential. This has a more negative electrode potential. So the electrons are going to want to flow away from the more negative towards the more positive. So since the electrode that is more negative is going to the electrons are going to leave that electrode, so that's going to undergo oxidation. So here we have this manganese is the more negative. So this is not going to have as much of a tendency to undergo reduction as this one. So because this is more negative, this is more likely to undergo oxidation. So we would have to flip this. We would have to reverse this to make it an oxidation reaction. And so here, since this is more positive, or less negative, if you want to think of it that way, this one is less negative or more positive, and so therefore the electrons are going to want to go towards this electrode here. So remember the gain of electrons. If the electrons are going towards this electrode, then that's gaining electrons. That's going to be reduction. So we already have this in the form of a reduction reaction. So between these two, this reaction has a higher tendency, a larger tendency to undergo reduction than this one. So this one will keep in this form here with a negative 0.23 volts. This one we're going to have to flip into the oxidation reaction. And so that's what we did here. So oxidation is going to happen at this electrode. So we have manganese solid, and that's going to lose 2 electrons to form manganese 2 plus aqueous, and then 2 electrons. And then the other electrode has the redox going on. Remember, cathode is where redox happens. Another mnemonic device that you may want to use to help you remember what happens at each electrode. It's a red cat, or red cat and an ox. Red cat and an ox. I'll go ahead and write that down really quickly. Here we go. So we have red cat and an ox. Red cat and an ox. So reduction happens at the cathode, and at the anode you have oxidation. So that's another mnemonic device that you can remember. So now that we have oxidation happening at the anode, and this is our oxidation reaction happening, and here we have reduction happening at the cathode, and here's our reduction reaction happening, and here are the respective electrode potentials. Now, when we add these together, you'll notice that I crossed out the 2 electrons. So I have 2 electrons here as a product. I have 2 electrons here as a reactant. Those are going to cancel out when I add these two equations together. And here I get the full equation, which is nickel 2 plus aqueous reacting with manganese solid. That's going to produce nickel solid, because the manganese is going to transfer 2 electrons to the nickel. The nickel becomes solid, and then by transferring losing the 2 electrons, it's going to be manganese 2 plus aqueous. And so just like with the Hess's law and the rules for enthalpy changes, and what do you do when you reverse a reaction, or what do you do when you multiply by a particular factor, that also applies here, with the exception of multiplying a factor. If I multiply this by 2, it doesn't do anything to the electrode potential. The electrode potential stays the same. However, if I reverse my reaction, then I can change the sign. But you don't need to do that. I'll show you a couple of ways to do the calculation. So here I have the two half reactions. I have oxidation, reduction, add them together, and I get the full equation here. And so what do I do with the electrode potentials? Well, I plug them into the equation here that we've used before. So I can find the standard cell potential by taking the electrode potential at the cathode and subtracting out the electrode potential of the anode. And so here I have these here. And so I can plug these into the equation. So negative 0.23 volts for the cathode. That's this. Minus negative 1.8 volts for the anode. So that's here. And so when I subtract a negative, I get a positive, and then I add those together and I get 0.95 volts. So the standard cell potential for this reaction, for this redox reaction, is going to be positive 0.95 volts. And so because the standard cell potential is positive, that's going to be spontaneous. Now, another way you could do this is, as I was saying before, is just like with if you flip the equation, if you flip the equation of a reaction, then you change the sign of the enthalpy. So if you have a delta H of the reaction, if it's negative and you flip it, you reverse the reaction, you would make that positive. You would just change the sign. So the same thing happens here. When I take my manganese, notice I didn't do here. The reason I didn't do here is because you can take the original electrode potentials as they are given for the reduction reactions and plug them into the equation. And because you're subtracting the anode and oxidation happens at the anode, this negative sign is what changes the sign of whatever you're given. So the reversing of the sign here is taking place by subtracting the anode, which is where oxidation is occurring. So what I could do here is I take this equation here, I flip it, and I can just adjust let me use a different marker. I can change the sign. So I make that positive, and then once I make that positive, I just add those together, and I get the same answer, 0.95 volts. So that's an easy, quick way to do it. So if you flip whichever one of these you flip, you got to change the sign. So the one you're going to flip is the one that's more negative, because again, the more negative electrode is going to be the one where the electrons are going to be pushed away. They're going to leave that one, and therefore the leaving of electrons is where oxidation takes place. And so you're going to have to flip that to make that an oxidation half reaction. Okay. So the key thing here is any reduction half reaction that's listed is spontaneous when you're paired with the reverse of a half reaction that appears below it. So another thing we could look at, what is this referring to? Well, it's referring to this sort of thing right here. So you'll notice that this is a list of the standard reduction potentials of half cells. And you'll notice that this is common. You can find this on the internet. It's in your textbook probably, or your professor gave you one. But you'll see here that they're listed according to their redox half reactions. So these are all redox half reactions. And they start with the most positive up above. So the most positive electrode potentials are on top. So what did we say about most positive? Most positive is where they're going to have the electrons are going to be attracted most, because negative electrons are attracted to positive. So the higher you are on the table or the list here, the more likely, the more you have a tendency to undergo reduction, the gain of electrons. And as you go down, you become less positive or more negative. So that means as you go down the list, you have less tendency to gain electrons and a more tendency to lose the electrons. So you can use this list and figure out what half reactions go together to form a spontaneous reaction, right? So here is a good table to use. So that's what this is referring to. So any reduction half reaction, so choose a reduction half reaction on the list. So any reduction half reaction listed is going to be spontaneous. That means it's going to do the reduction reaction automatically when it's paired with what? When it's paired with the reverse of the half reaction that it appears below it. So what I was just saying before is on this list, right? If you're higher on the list, you're going to have a higher tendency of gaining the electrons. So if I take something that's high on the list and pair it with something below, anything below the one, let's say let's say gold here. So I take the gold here, it's 1.5, it's a positive 1.50 standard electrode potential. And so that is going to undergo, it has a good tendency of undergoing reduction. If I pair that with anything below it, right, anything below it has less of a tendency to be to undergo reduction, but has a higher tendency to undergo the oxidation. So if I pair gold with anything below it, that's going to be spontaneous, because the ones below it are going to are more likely undergo undergo oxidation rather than reduction. The gold would undergo the gold would undergo reduction more likely if it's paired with any reaction below it. So any reaction below on the list, you would have to reverse to make it into oxidation. So that's what this is saying here. So that's another way that you can use, another thing you can use to figure out whether a reaction is going to be in the what direction is going to be spontaneous. So we could use this as an example again. So here you can see nickel is going to be higher on the list than manganese. So because nickel is higher on the list, notice that nickel is more positive or less negative than manganese. So therefore, since manganese is lower on the list and it's again more negative, that means it's going to undergo oxidation more readily than reduction. So this is going to have a higher tendency to undergo reduction than this one. So this is the one that's going to undergo reduction. And so we would need to reverse this one to undergo oxidation, and then we pair that up. And that would be a spontaneous reaction. So I hope this is helpful. If you learned from this video, if this is helpful in any way, then please share this video, like this video, hit that like button right there, please. Also, make sure you subscribe to my channel, hit that notification bell. If you hit the notification bell, make sure you hit all so you can see all my videos and be notified whenever I put up a video. And finally, put a comment down in the comment section. Let me know what you think. And if you have any questions, I'd like to hear from you. Thanks for joining me, and have a great day.